In this lesson, we're going to talk about piecewise functions. A piecewise function is a function defined by using two or more rules on two or more intervals. As a result, the graph is made up of two or more pieces of similar or different functions. Let's say we want to graph this curve right here. Well, what we've got are three different rules over three different domains. We've got y equals negative x plus 1. We've got y equals x squared, and we've got y equals x plus 2. Now, the piecewise function is indicating a part of each domain over which we should graph that particular expression. So, for example, we should only graph y equals negative x plus 1 when x is less than negative 1. So we should only graph that part of it. So what we're going to do, we're going to put an open circle where x equals negative 1, like we just showed a second ago. And because we're not to include that point in the final graph because the domain says x less than negative 1. Now, we still want to plug an x value of negative 1 into the expression y equals negative x plus 1 because it's going to tell us where to put the open circle. So putting an x value of negative 1 into the expression y equals negative x plus 1 tells us that we're going to have an open circle at negative 1, 2. Okay? Now look at the next part of the piecewise function. We're going to include the part of the curve between x equals negative 1 and x equals 2, the part of the y equals x squared curve. We're going to have a closed circle at x equals negative 1, and we're going to have an open circle at x equals 2. We have a closed circle at x equals negative 1 because it says less than or equal to, but we have an open circle at x equals 2 because it just says less than. And then we're going to include all of the part of the curve in between those 2 points. Now, to make the graph as accurate as possible, we're going to determine the y-coordinate of the closed circle and the open circle. So when x is negative 1, what does x squared equal? It equals 1. And when x is 2, what does x squared equal? It equals 4. So that tells us that we've got a closed circle at negative 1, 1 and an open circle at 2, 4. And finally, we're going to look at the last part of the piecewise function. We want to include that part of the function y equal x plus 2 for which x is greater than or equal to 2. So we're going to include all the points on the line y equals x plus 2 to the right of x equals 2 and including x equals 2. So at x equals 2 out here, we're going to put a closed circle and we're going to include all these points. Okay? But we should know the exact location of that closed circle. And so the way we figure that out is we take this x value of 2 and we plug it into that rule to make sure we know exactly where it goes. We see the closed circle will be at 2, 4. So we want to take those 3 red portions and put them together as one curve. Now notice that there's an open circle and a closed circle at 2, 4. If that happens when graphing a piecewise function, the net effect is to have a closed circle. So the curve will move continuously through that point, and it'll look like this. And that's the graph of the curve. Now, something I want to point out to you, notice that the curve is discontinuous here, but it's continuous here. A curve will be discontinuous at the boundary point, like we see here, x equals negative 1 is a boundary between these 2 domains. A curve will be discontinuous if the y value of one of them doesn't equal the y value of the other. In other words, if the open circle doesn't land on top of the closed circle. But a curve will be continuous if that boundary value of 2 creates the same y value and allows us to put an open circle over top of a closed circle. Which leads us into the next question very nicely. Solve for k given that this function is continuous over all x element of the reals. Well, we see that our boundary value here is an x value of 1. We see that we're going to have an open circle there because it says x greater than 1, and we're going to have a closed circle there because it says x less than or equal to 1. Well, we want that open circle to land on that closed circle at an x value of 1. Now, we're going to see two solutions here. One of them is long and explains why the shorter version works. I just explained why the shorter version will work. The shorter version is just to let 3x plus k equal x plus 5 at x equals 1. And if you understand that, you don't have to watch what we're about to do. But let's just watch this long explanatory way. It's not that long. We'll start by graphing the part of the piecewise function that we know, which is the second part. So we're going to start by graphing this part of the function, and it looks like that. Now, we don't know exactly what this looks like, so let's pretend that we let k equal 0. And if we let k equal 0, that upper part would just look like this. Now, are those two continuous? Is that one continuous function? Absolutely not. There's a gap there. And we can't have that if we're going to call it continuous. So we're trying to figure out some value of k, which is going to allow this closed circle right here to land right on top of that open circle and make it continuous. So we know that the open circle is at 1, 6. So we want to solve for k such that the closed circle ends up on 1, 6. And so in other words, we want to solve for k such that when we plug x equals 1 to y equals 3x plus k, we get y equals 6, because we know that's the bottom part. In other words, we want 3 times 1 plus k to equal 1 plus 5. Okay, and we end up with k equaling 3. Now, do you have to show all of, oh, and by the way, this is what the curve looks like. This is what the function looks like if k equals 3. Do you have to show all of that on a test? Absolutely not. Here is how you answer a question like this on a test. Right, like that. All you do is you say at x equals 1, which is the x value creating the boundary of the two different rules, I need 3x plus k to equal x plus 5. Well, that means 3 times 1 plus k equals 1 plus 5, 3 plus k equals 6, k equals 3. And that's the answer, whole answer. Now, let's solve for a and b given that this function is continuous over all real numbers. Well, there's the first rule and the second rule meet at a boundary x value of -4. One's an open circle, one's a closed circle. So I'm going to want 2x plus 7 to equal x squared plus a when x equals -4. So let's do it. 2 times -4 plus 7 equals -4 quantity squared plus a. Ultimately, -1 equals 16 plus a, and a is -17. Well, that was easy. So now, since I know a is -17, I'm going to want the second rule to equal the third rule at the x value at which the open circle and the closed circle might meet. What's the boundary x value there? In this case, it's 3. I want x squared plus a to equal 5 minus bx at x equals 3. Okay? But remember, what's neat about this, so like it says here, x squared plus a equals 5 minus bx when x equals 3. But what's kind of cool is we already figured out that a is -17. So we're really saying 3 squared minus 17 equals 5 minus 3b. Well, we can solve that. b ends up equaling 13/3. And so we can say the function is continuous over all real numbers if a is -17 and b is 13/3. And finally, let's do a word problem question and talk about a country we all want to go on vacation, Mathland. Mathland has a taxation system where residents pay 25% tax on the first $50,000 of income. They then pay 35% tax on the next $100,000 of income and 50% tax on all income after that. Let's get a simplified piecewise function to represent the system. Well, the first part's fairly easy. Suppose a person makes less than or equal to $50,000 in income. If that's the case, then their tax will simply be 0.25x. 25% of their income. This is a pretty simple rule for such a person. But what if someone makes more than that? Well, if a resident makes more than $50,000 but less than or equal to $150,000, then what happens is they pay 25% tax on the first $50,000, and then they pay 35% tax on the income above 50. They never pay both 25% and 35% on the same dollar. The first $50,000 have been taxed at 25%. They're done. There's not more tax there. The 35% tax is just on the new money after the 50,000. In other words, the 35% tax will just be on X minus 50,000, the income they make above 50,000. So 0.2 times 50,000 is 12,500. 0.35 times X n times negative 50,000 is this expression here, 0.35x minus 17,500. And putting them together, we end up with 0.35x minus 5,000. That is how much tax a person pays if their income is in between $50,000 and $150,000 at where their income is represented by X. And finally, some people really make a lot of money. And these people are going to pay 25% on the first 50,000. Then they're going to pay 35% on the next 100,000. So let's think about this. $50,000 they paid 25% tax on. They then paid 35% tax on the next $100,000. Well, you can't get taxed on the same dollar twice. So what's happening is their first $150,000 of income has already been taxed. No more tax on that stuff. So the stuff that's getting taxed at 50% is their income, which is X, minus that $150,000, which has already been taxed. 0.25 times 50,000 and 0.35 times 100,000 give us these two values here. We distribute 0.50 into the bracket and get this expression, and we collect our like terms and we get this expression right here. So we've got three different rules for three different levels of income. For people between 0 and 50,000, we say the tax will be 0.25x. For people between 50,000 and 150,000, we say the tax will be 0.35x minus 5,000. And for people whose income is greater than 150,000, we say their tax will be 0.5x minus 27,500. Now, notice the lower bound of the domain is 0. It's not possible to have income less than 0. Also notice that the X value of 50,000 is only included in one of the steps. Someone using this formula needs to know which step to go to. So you can't put 50,000 in both the first and second step. You need to include that value in one of the lines, but you don't include it in both. And similarly, the value of 150,000, you want it to be in one of the steps, but not both. It's the same value in both steps, but you want to include it in one of the steps, but not both. And that is our lesson on piecewise functions.